Yield monitors are not perfect systems, although they do provide an excellent indication of yield variability across the field. Let's take a look at the different types of errors that can be induced or can occur on yield monitoring systems and provide some groundwork for how we can try to eliminate or prevent these sorts of errors. First of all, on the impact sensor itself, there's a variety of things such as grain roughness, paddle clearance, blockage maintenance that can cause the sensor to lose response. Remember, the sensor has to physically deflect when grain hits the impact plate. If the backside of the plate is gummed up or blocked with crop residues or biomass material, then all of a sudden the impact plate's not able to do its job and will result in lower yields than expected. Additionally, the combine will induce a lag between when the crop enters the header and when it reaches the top of the clean grain elevator. This is caused by the physical effects of the combine, things like the elevators, augers, cylinders, and sieves. And the result of this is yield data that's delayed and can cause striping of the yield map. Common software today will help us eliminate this by adjusting the time or the position of each GPS point based on a given offset or lag time for a particular combine. Additionally, the combine tends to act as a smoothing machine. So if we have sharp differences in yield data, such as when we cross a waterway or go through an area that may have had a fence line previously, then the yield monitor will tend to smooth out those sorts of sharp responses. What this does is limit some of the usability of this system for long-term decision management. We do have to know a little bit about the field so we can see deeper into the yield data and identify those particular areas of sharp change. Additional factors that will impact error include things like the combine tilt or the bumpiness in the field. If the combine is on a slope, then all of a sudden the grain is not hitting the impact sensor with the same type of consistent force. This will induce a given percent error based on how aggressive the slope is. The moisture sensor can also be a source of error if it's not well calibrated, or if there's free moisture from wet grain or foreign material in the grain. This will change the moisture sensor's ability to accurately estimate the true moisture. In doing so, it becomes one more added factor of overall error. Speed measurement is also another factor of overall error, particularly abrupt changes in speed when either when the combine either starts from a zero position or when it quickly comes from a stop at the end of a pass. Speed errors can be overestimated or underestimated in these conditions. Since speed is used to calculate the overall area of coverage, this becomes a significant problem or error source in the final yield calculation. Estimating the actual cutting width or header width of the combine is also a common error. This typically occurs with soybean or wheat heads, where the header might be 30 feet wide, but only 29 feet of crop is actually being engaged with the head. This reduction in total header engagement causes a direct error in yield calculation. Additionally, you can have things like simple errors in calibrations or poor calibration curves or calibrations that aren't updated in a timely manner. As a rule of thumb, calibration curves should always be updated at least once a year per crop. So as you move from corn to soybeans, you need to have a separate calibration curve. And calibration curves should also be updated anytime you have a significant change in material properties. So if you have a 4 to 5% change in grain moisture, you should definitely recalibrate the machine. If you get into a significantly different test weight variety that is potentially 4 or 5 pounds per bushel different in test weight, then this would also require a system recalibration. Variable grain properties, just like I mentioned with moisture and test weight, those sorts of things can absolutely affect the accuracy of the yield monitoring system and must be taken into consideration by the user. So let's talk in a little more detail on this this lag or lead time error caused by the grain flow into the combine. When the cutter bar first is lowered by the operator, and it'll take some sort of time called stage 1 and for it to reach the crop or begin to engage the crop. During stage 2, the system will begin to engage or cut the crop, and we should begin to get some of the very first yield readings. Now these will be very low yield readings because the combine's not yet full of grain or not yet in a steady state flow condition. During stage 3 is kind of the ramp up of that the combine to begin to get full flow rate of grain back into the clean grain elevator and up to the mass flow sensor. Stage 4 then is when we finally hit that steady state sort of condition. Now in typical systems, stage 2 to 3, from the time you engage the crop with the header until you get full flow rate of grain up to the clean grain elevator, it's typically anywhere from 10 to 15 seconds, and with 12 to 13 being a pretty good average number. The same sort of situation happens on the back end. When you exit the pass and exit harvesting grain, after the cutter bar leaves the crop, you have a certain amount of time when the combine is still operating with a full set of grain flow and still transferring flow up to the clean grain elevator into the mass flow sensor. Eventually, though, the combine will begin to empty out, and you'll have a decayed response of the mass flow sensor. Now, commonly, we want to avoid this sort of lower yield effect caused by this. So when we enter into, or excuse me, when we exit a given pass, the rule of thumb is to lift up the header so that we disengage the mapping system and prevent this drawn out or decayed flow rate of material from resulting in a mass flow measurement. We also mentioned that yield monitors aren't the best at actually quickly responding to changes in yield. The diagram shown here presents kind of a targeted flow, which is the pink line, and the mass flow seen by the monitor, which is the blue lines. And you notice that there's a decayed response or a slow response of yield to a step response change in mass flow rate. And what that means for us in a practical sense is that the yield monitor is not going to be able to pick up really small or short variations in yield. It's very good at giving us overall trends across the field and some high-level variability across the field, but not as good with giving us real fine resolution responses. Here's a look at a different sort of response, and you see the same sort of indication where the dark blue lines or the monitor flow rate take a longer time to ramp up to the actual flow rate of the system. There's then a decay when the actual flow rate drops, and you can see that the monitor begins to filter out this data. Same sort of thing when you put a sawtooth type yield response into these combines. So again, they do great when they're talking about field scale variability, but they aren't well suited for really small changes or variability in grain. Topology or slope is also a major impact on the overall accuracy of yield monitoring systems. And if you think about the location of a impact sensor, it's relying on the impact force of grain hitting the impact plate. Well, if the combine is heading uphill, for example, all of a sudden the grain has to overcome gravity in order to impact the mass flow plate. The effect of gravity, essentially taking momentum away from the grain, will induce reduced or errors in yields in those sorts of conditions. Likewise, when you're heading downhill and gravity is helping the grain, you'll have an overestimation of yield in those areas. So it is something to take into consideration, although the errors won't be extremely significant, on the order of 2 to 5%. They certainly are errors that can pop up when you're faced with yield harvesting data or yield monitor data in areas of highly diverse topology.